Thank you so much for joining us for the April edition of the MIT.nano Seminar series. We are honored today to welcome Professor Alán Aspuru-Guzik from University of Toronto. He will present to us a seminar today titled, "There's No Time for Science as Usual, Materials Acceleration Platforms." I'm truly honored to introduce Alán. He has been a friend for a long time, but also an extremely distinguished individual. Alán's research lies at the interface of computer science with chemistry and physics. He works in the integration of robotics, machine learning, high throughput quantum chemistry for the development of materials acceleration platforms. These self-driving laboratories promise to accelerate the rate of scientific discovery with applications to clean energy and optoelectronic materials. Alán also develops quantum computer algorithms for quantum machine learning and has pioneered quantum algorithms for the simulation of matter. He's jointly appointed as a professor of chemistry and computer science at University of Toronto. He's a faculty member at the Vector Institute for Artificial Intelligence. Previously, he was a full professor at Harvard University, where he started his career back in 2006. He's currently the Canada 150 Research Chair in Quantum Chemistry, as well as CIFAR AI Chair at the Vector Institute. And in addition to all of that, he's a co-founder of Zapata Computing and Kebotics, two early-stage ventures in quantum computing and self-driving laboratories. Without further ado, I introduce you to Alán. Alán, please take over and tell us a great story like you usually do.
Thank you. Vladimir, it's a pleasure to see many people in the room. It's not the same as being there in building 33, but I see Klaus, Mark Bade, Jin Kong, and many others that I've interacted over the years, James Banal. So nice to see you all. So let me tell you about what I've been doing actually since I moved out of the Boston area. I guess I was just telling Vladimir, we started an experimental lab and things of that sort. So let me just tell you about these so-called self-driving labs. And the first reason is why. It is incredible, right, that we have compressed the development timeline of a vaccine. And by the way, I got my second dose of the vaccine yesterday, and this is the reason why I might be a little bit slower today, to a year. People thought that was incredible. There was a paper in the New York Times thinking the vaccine was going to take, 7 to 8 years. Well, guess what? We need to do this for materials, if anything for energy, but also for water filtration and many other applications that are intimately related to climate change. And, as our, the Prime Minister of Canada, also the President of the United States just recently renewed their vows to lower emissions. We need to do our side from the technology side. So the question here is it possible to take the materials development efforts that usually take, say, 25 years and several tens of millions of dollars to get to market in a compressed timeline, maybe of a year and $1 million, right? So that would be the timeline of COVID, kind of post-Moderna, COVID vaccine post-Moderna. And the $1 million means, the FTEs that you need to spend on the reagents, assuming you already have built a machine that allows you to accelerate this. And we think this could potentially be done by taking the tools that we already know how to use from high throughput screening, but making them smarter, so to speak, augmenting them with AI. And also seeing of the entire discovery protocol that goes from the ideation of a molecule to the synthesis and testing, potentially even scale up and even manufacturing, as an entire platform where you're really connecting all of the stages together, the same way it's done in pharmaceutical drug discovery, that you're thinking about all the stages as tightly as possible to lower the cost and the time. This means that we, material scientists, chemists, engineers, we need to be more multidisciplinary, embrace the tools of computer science, embrace the tools of robotics, and use them all together if this hypothesis I have is true. So in this perspective, with my former student, Benjamin Sanchez-Lengeling, he's now there in Cambridge, working for Google, doing interesting works on AI for prediction of smell with Alice Wilschko. So he and I got this perspective just before he left for science, where We're trying to talk about, our own work on organic flow batteries. I've spoken at MIT about it before. We proposed with Roy Gordon and Mike Aziz a new class of compounds for doing energy storage in solution. It's still a slow process because we did everything the traditional way of producing the candidates with a computer, synthesizing them, making devices by hand, etc. We got one side of the battery to work, published in 2019 in June. Now we still think about the other side of the battery. And what I argue is if we had done this in an automated fashion, maybe we could have gone faster. So let's see how far one can go. Now, no pressure. MIT Technology Review just recognized these AI discovered molecules as a top 10 breakthrough of 2020. And there are excellent players at MIT that work on this space. Your own Klaus Jensen, Conrad Coley, Regina Barzilai, Rafael Gomez Bombarelli, and I'm pretty sure I'm missing many others, are key leaders in the space. Having said so, we're very proud also that the Vector Institute, the University of Toronto, where I work at, but also our startup Kebotics and my collaborators are in Silicon Medicine were actually highlighted by MIT Tech Review. And they claim, availability 3 to 5 years, no pressure. So why is this? So because this is a diverse audience, maybe material scientists and engineers and all other different areas, we kind of want to look at these three of what is AI. And, we're not talking about general intelligence, although I will discuss general intelligence at the end. But rather shallow intelligence, and in particular, deep learning, Bayesian modeling, and robotic process automation are going to be the three areas that I'm going to be using. But I believe the young people in the audience here will be able to, and of course the faculty as well, and researchers will be able to actually use many other areas of AI. AI is a field as big as chemistry or material science, many places to draw from. And I believe the more and more we integrate our fields, the more we will be able to use different tools from there. So what is the big deal, right? I mean, people have done quantitative structure activity relationships, QSAR, for a while, both for material science and pharma. And if you think about them, what you did is you picked some set of handcrafted features and be a generalized linear model to predict from such a molecule a particular property. This is usually a regression or classification problem. What the deep learning revolution allowed is to have this kind of modular hierarchical type of functions called deep neural networks that require more data, but allow you to actually look at the data at different scales. And they are fitted with state-of-the-art technology like backpropagation and very good loss functions that allow you to actually have these very generalizable functions with many, many parameters. Technology has been advancing really quickly. And who am I to talk about that? To MIT, one of the leaders on this. Well, the University of Toronto Computer Science also has been a deep developer of this over the years, as you know. So the difference here is that now the representation, I'm going to call it the Z vector, or sometimes called the latent space vector, will be learned by this transformation, right? So it is bound perhaps to be better than any handpicked one if you have enough data. So we started on this space very early on, and this paper is bound to be my most cited paper very soon. Basically, the work done by my now colleague David Dubenot, Rafa, which is now at MIT, Ryan Adams, my former colleague that is now at Princeton. So all of us moved around. But bottom line is that we took the so-called circular fingerprints, binary fixed length vector representation for molecules that is hierarchical. First looks at atoms and next nearest neighbors, next nearest neighbors, and built a continuous differentiable version that has hidden weight matrices that are these parametrizable transformations. And that's kind of started like a huge cottage industry of graph networks for molecules. So tons of people are working on it. Many computer scientists now use this as a kind of benchmark. And it's pretty cool to see them citing these molecular benchmarks as part of their development of the methodology of this field. So I will argue that one of the most important things you can do is think about the representation. You can even, ultimately you would like to learn from the quantum mechanical wave function of the molecule, right? That will be the most information-rich representation. But there's all sorts of other representations listed here that people have used over the years. And I'll tell you about string representations maybe in this talk as well, and other types of representations. To talk about it, I really like this paper by Rishi Kondor, where he took our convolutional networks, but now made them invariant to graph invariant. So he converted it into a tensor method. And you can see here in the left-hand side for this hard clean energy project, which is a data set of organic photovoltaics that we started in 2006. It's kind of like cool that they're using my retro data set for this now as a benchmark. But this data set shows you that, even if you use very simple regression models, and you saturate, right? You saturate even if you actually optimize the parameters of the neural graph fingerprint. But if you use the second order convolutional network that they developed, you get a much better results in MAE and RMSD, which tells you, in my opinion, that the representation is key, right? So if you want to make improvements, you want to think of the model, but also the representation. So now let's talk a little bit about material science. This connects actually to the beautiful work of Vladimir and my colleague Mark Valdo at MIT as well, which I collaborated with in the past. And Rafa, of course, Rafa Gomez. So this is a paper by Rafa that where we worked about 4 years ago. This is the one that inspired me on self-driving labs in developing these so-called temperature-assisted delayed fluorescence emitters. These are molecules that, unlike traditional organic molecules for light-emitting display applications, have the singlet and the triplet at a very close energy, okay? Which basically means that the triplet can thermally activate, have reverse intersystem closing, and fluoresce from the singlet, making it what is called the third generation display. So this was pioneered by Chihaya Adachi at Kyushu University. And around 2014, we're trying to find molecules for TADF emitters. This is a famous figure from that paper from Rafa, when we show how we took chemical space and down-selected chemical space by means of AI and filtering and voting to synthesize and test 40 champion molecules, out of which we ended up with 3 candidates, good enough for a Nature Materials paper, but they are not in your cell phone, otherwise I'll be driving a Tesla, right? And that teaches me that this funnel is terrible because, even if I can calculate millions of molecules with AI, if I can only make 40, then I'm in deep trouble. So around that time also, we started thinking about the so-called generative models, right? You can see here this which face is real.com generation of machine-generated faces. Very interesting because you're generating data from a non-trivial probability distribution, right? So these generative models, instead of just doing this regression task or classification task, generate this joint probability distribution between X and Y. So we were lucky to pioneer the use of these models for chemical space. And in this paper, use them to use a model called autoencoder, which is very nice. It's kind of like in some sense, a weird model, because what it does, it takes representations of molecules and just tries to represent them back by compressing and decompressing in a low dimensional, well, in this case, 200 dimensions, continuous differentiable space. What we did is basically add another model, in this case, a Gaussian process, tied to that particular low dimensional space, and optimizing that model. And what is really cool about it is that this model that is trained on this representation that was trained with about 250,000 molecules, as you maximize the properties of that model, and then you try to decode, you can use the decoder part of the autoencoder to figure out what molecule was there, solving the so-called inverse design problem. Since then, obviously, several methods. People have used generative adversarial networks, reinforcement learning, RNNs, you name it. Many different approaches to generate these molecules from a probability distribution of potential molecules. The game is to make them more synthesizable, as you will see. The game is to make them materials, etc. This is where the tech review breakthrough technology came, right? In this paper, Nature Biotechnology, with our collaborator Shaborankov from Nature Biotechnology, it took us 46 days to use the generative models combined with computational filters, as well as basically not automated, but high throughput by hand type of biological experiments, real rats and so on, to actually propose the DDR1 kinase inhibitor, kind of a low-hanging fruit of computational drug design, but still good enough to be a Nature Biotechnology paper. Since then, beautiful work has appeared by many authors around the world, including, of course, your own Regina Barzilay in a Cell paper, where she and her collaborators have developed antibiotics. Since then, we've been quite busy. With my collaborator, Yu Sung Yoon, we started working on generative models for crystals. So here, you can see here a very nice model that we came up with for using an autoencoder type of architecture to generate molecules, compositions of vanadium oxides that could potentially be catalysts low enough in the convex hull of the materials. And so basically you might be able to synthesize this if you think about it as a material scientist. And we also did generative adversarial networks as well as autoencoders. And then just appeared in Nature Machine Intelligence a couple months ago, maybe, this paper where Zhengpeng Yao, collaborating with Randall Snur, I think did what is perhaps one of the most complicated, at least in my group, or state-of-the-art in my group, generative models, because we combine kind of crystal structure type generations with molecular generation to generate these sponges, these molecular sponges that are called metal organic frameworks. Of course, many people at MIT are experts on it, like Mircea Dinka. And these materials are used for many applications, including catalysis. In this case, we optimized and predicted perhaps some of the best top performers for gas separation according to our calculations. Now, of course, you can keep using these generative models to predict molecules, but the rest of this talk is pretty much going to be about how to make them. So I know I'm supposed to speak for 40 minutes or 45 minutes. So I'm going to just tell you a little bit about other AI developments, but then I'm going to skip a few, okay? So let me just talk about representations again. We're very excited about this paper that, right now is the most downloaded paper of machine learning science and technology. So what we do in this paper is Mario Kren, which is actually a quantum optics researcher in my lab, and he was looking at how we represent molecules, and he said, look, the graphs that I used to represent my quantum optics experiment are 100% representable, whereas the smiles have all these typos. Like if I have a string that represents a molecule like this, the so-called smiles, you can see here CNC, this is CNC, parenthesis C is this particular group here. And you continue moving around in the molecule. The so-called selfies that you see in the bottom are just a rewriting of this type of grammar in such a way that the strings are 100% representable. Any random shuffling of a selfie will also be a valid string. And that's very, very important because now your machine learning model doesn't need to learn how to do grammar. It just needs to learn how to represent molecules, okay? So this is the two principal components of the latent space of one of these models, an autoencoder. And you can see how in the smiles, most of the molecules are invalid, whereas in selfies, they're all valid, giving you 2 orders of magnitude more density of molecules in the latent space of this autoencoder. Also giving you many, many more diverse molecules in generative models. So I will say selfies have really enabled a lot of technologies in my lab. And one of them that I'm very excited, and by the way, you can just use selfies like as a single line installation. You can just download selfies, convert your smiles to selfies and back, and there you go. So I recommend you to try them as part of your baseline studies, and maybe even your main representation. We really use it as our main representation. I'm going to skip this ICLR paper and tell you about some of the recent papers. Where we have a paper, you know what? I'm going to skip this. There's this paper called Stoned, but I'm going to skip that to have time to talk about robots and then have time to have Q&A. Okay, so feel free to ask me questions about selfies and answer you more stuff in the Q&A maybe. Well, let's just move on to the experimental side. Okay, so as I said before, I mean, I took the opportunity of moving, after moving to Canada, to really start an experimental laboratory and try to test this hypothesis that I've been thinking about for a long time, since that paper I told you about with Rafa, of what will be the case if you actually took a lab and you rebuilt it, and you took the physical chemistry piece, the analytical chemistry piece, the lasers and the synthesis piece, etc., and automated and put them all together in the same room. So this came from a workshop that we led in Mexico City under the Mission Innovation Platform, under the Paris Agreement. So I recommend you to read that workshop report that we wrote with Christine Person that talks about how to integrate all these elements. And since then, several invitations to different perspectives and so on have allowed me to work with my group and write about different aspects of them. And you can see here our different papers about different aspects, the AI aspects, the experimental aspects, etc., of these materials acceleration platforms. And this is where we connect also with your colleagues at chemical engineering. I mean, Klaus Jensen leads with Connor Coley and others a very large collaboration on DARPA, on the same DARPA program as us. So our DARPA program, Accelerated Molecular Discovery, we are the performers of my team, the Toronto team, called our project Madness. And the reason we call it Madness is because I guess we have a set of mad and excited collaborators, Marty Borg, Lee Cronin, Bartosz Żuławski, and Jason Hein. So for the remainder of this talk, most of the work I'll be showing you is done in collaboration with their groups. And the idea is to actually build self-driving labs. But for which application? Well, we hark back to our friend and visionary Chihaya Adachi. He has been dreaming for a long time the use of organic solid-state laser diodes. So will be the coherent emitter version of the organic LEDs that we were talking about. And the reason we picked the organic lasers is because Chihaya has done only, perhaps 30 or so different molecules reported. And there's not many groups working on it. So we think if we want to show that a materials acceleration platform has some sort of advantage, we wanted to start in a field that there's very little done. What happens to them? Well, they burn, basically. It's very hard to drive with so much energy, this lasing process from an organic film. Okay, but they could be used for many applications that are listed in this slide, but this is a very more basic research problem. But now you might wonder, okay, how are you going to automate the synthesis of organic molecules, right? I mean, in some sense, we're lucky compared to materials because there are rules to make them. And furthermore, you could potentially flip organic chemistry on its around and think about organic chemistry the same way biology thinks about it. If you think about the huge advances that we have had in biology, they come from the fact that we can actually sequence and automate DNA and proteins, right? We can literally make them piece by piece. And it is because nature uses these iterative coupling schemes. They put a block, then the next block, then the next block. Obviously using enzymes and other tools that we don't have necessarily at our hand for the robots that we're going to be using, but we're going to use automated chemical synthesis. And this is where the work of my collaborator and friend, Marty Borg, has really inspired us, because Marty has used this technology, iterative coupling schemes, in particular, this very simple metaboronate protected Suzuki coupling that does carbon-carbon bonds. By being very smart about picking your molecular library fragments, then you can get away with using one or perhaps 2 or 3 organic reactions for your entire chemical space search. And in this case, we'll be using a single organic reaction using this methodology by Marty, which shows you here in some of these papers, produces molecules that are very similar to what we use in organic electronics. So my lab was started as a computational lab. So the quote-unquote easy part for us is the modeling of the necessary but not sufficient molecular properties for having an organic laser, right? You need to avoid, non-radiative relaxation, avoid excited state absorption, avoid intersystem crossing and triplet absorption. And computationally, you can do that by actually having these parabola models coupled with each other and using path integral calculations to calculate the wave function in them and actually calculate the rates. Work that I've done in collaboration with many others, including, for example, a lot of work I did before when I was in Boston with Mark Bade, which I think is here in the room. So, but what we do here is a little bit departing from the beautiful retrosynthesis efforts of my colleague Connor. So Connor has been really thinking a lot about, together with Klaus and others at MIT, on the complicated problem of retrosynthesis. Here, we're thinking in something simpler. We're thinking about forward synthesis. We take our blocks, we use AI to produce the chemical space available by the Suzuki coupling, and have a space of the order of 100 million molecules with about 300 blocks that we purchase. So what we do for the AI, we work with Bartosz Żuławski. He leads that. He uses very simple neural networks to actually, what is very important is getting the right data from the literature and the right data from experimentation that I'll be telling you about, to actually train these models and figure out what are the incompatible and compatible groups that will allow us to make successful Suzukis that allows us to actually prune the synthesis space. And then our computational search only happens in the 100 million molecular space. For that, then we use active learning to actually use quantum chemistry and DFT to screen the promising targets, and then some of them experimentally testing between 15 and 30 per day if my robot ran 24/7. We have had many runs, but it is still magic to get the robot to run 24/7. So I'll tell you about results from runs that are happening. But the good news is that after my lab got kickstarted at the middle of 2018, with COVID and all, we've been learning how to make sure these chemical synthesis robots are maintainable. It's a lot of work in that. So that's another lesson for these materials acceleration platforms. Having said so, we're very proud of standing up this computational toolkit, in this case, for predicting the absorption and emission of our molecules. Here is a babrionically resolved absorption and emission spectra of one of our molecules. That's an example prototype for organic lasers. And therefore, computed, if you can see, for those computational chemists in the audience, and again, I try to refer to all my colleagues at MIT. Troy Van Boer is one of the pioneers of doing all of these things as well. So in this particular case, you will do something like this. You will use excited state methods such as TD-DFT, calculate the parabolas, the ground state and excited state Hessian. And that allows, it's about 13 hours in a CPU. But now, you know, the work of Stefan Grimme and many others allows you to actually reduce the work to a semi-empirical workflow of 15 minutes, which really makes it to us very, very easy to screen chemical space to find the right molecule. So again, this is kind of like the metabolite, you know, sequential building of these building blocks. A lot of the chemistry has to be modified from the hood to the robot. And that's part of the story here, right? So which robots? So we don't know exactly what's going to be the robot in chemical synthesis that's going to win. Here is a machine from Marty Burke that we replicated and we have now running in Toronto. Here is our ChemSpeed robot synthesizer at Toronto. The computer, which replicated in Vancouver and now in Toronto very soon. Vancouver assembled ours, is shipping it to us. This is Jason Hine. And then this is the N9 platform that we used with Jason Hine to do thin film discovery earlier on last year in a Science Advances paper that I should be listing here. So we are agnostic about the platform. Okay, every lab has a different one, and we think that the chemical synthesis will be a melding of all of this. So for example, at Marty's lab, we're about to finish a paper in collaboration with Bartosz and him on the optimization of general conditions for the Suzuki couplings. So we take fragments like this, we do several rounds of optimization. Now this is an outdated slide, so we have several rounds. We were really going and optimizing the general conditions for the Suzuki coupling. Because if you have general conditions, this allows you to be very similar to peptide couplings or DNA synthesis, where you can just basically go ahead and run. So basically that's something that we're working on. So how does our lab in Toronto look like? Well, we have setups, very lucky to have had Kazuhiro Hotta from Mitsubishi Chemical come in and assemble these ultra fast setups. Martin Seifert, that came from the group of Guy Bassan, has been key to work with Tony Gu, coming from the group of Mark Baldo. All of them together, also with many other group members, built this machine. And I have to give them all the credit because I'm a computational person. And I come into the lab and I ask them, what is this? What is this pump doing, guys? I mean, they built everything, right? So I was just giving the general direction, right? But this is an example of the robot that, again, MIT graduate Tony Gu spent a lot of time working on. This is our synthesizer that allows us to kind of like cook chemistry. For those of you familiar with the liquid handlers in chemical in biology, you can think about this as a liquid handler that is much more precise in terms of powder dosing, and is also able to cook at pressure and so on. So a lot of the problems that we have had with these are powder dispensing. So we moved to a solution model. Although you see it here, powder dispensing, and now adding solvent to the reaction. So this is an early video that we did, but now we have much more, control and understanding of this. And as I understand, we're really running a run, I think if not this weekend, to finish a paper that I'll be telling you about. So that's the good news, that the robot is now kind of like more routinely running as we learn how to change the parts that break down every once in a while. So what we built in the back is this complicated pump system that allows us to draw from the back of the robot. I mean, let me show you here. We have a little line that goes into this HPLC and then goes into these diluters over here that allow us to inject into this kind of boxed laser here for doing photoluminescence lifetimes. And also this large box that you cannot see over here that does excited state absorption setups. And these are real experimental data that came from an entire synthesis and characterization run in my lab. This is a molecule as it came out, and you see here the absorption and emission spectra of the molecule, these interesting features here, as well as its time resolved PL lifetime. So this is kind of an interesting lab again, organic chemistry, analytical chemistry. and now also ultra fast, right? So you can see here, our chromatograms, and then how we select from the different fractions, and then use a semi-preparatory column to actually draw again from our vials here that are here in the ChemSpeed, and then run them by the ultrafast. And the whole process takes about a day and a half for about, say 30 molecules or so. Okay, so give or take, that's roughly our throughput. This is an example of a run that was in the lab maybe 6 months ago. 4 boronic acids against 10 boromidas. This is one of our test runs. You can see here which ones have high product conversion, which have low product conversion. Some had no product. These were not really optimized at the level of using the AI of Bartosz yet. So we're going to be running those experiments to see if we could have weeded out those 4 that showed no product. It could also be that the product was there, but it was actually, precipitated. So anyway, without skipping a lot of stuff, because this is a paper that is going to come out very soon in the archive, hopefully maybe in a couple months or so. We're trying to see if we can push this last run I told you about to maybe in a month. This is really the result of about 40 molecules that we did for an organic laser optimization for a single step synthesis, okay? A core block and many ligand blocks. So this way we skip the separation process and the multi-step synthesis, but we were able to actually find molecules that have a low PL lifetime and a high quantum yield at the color region that we want, that are superior to the base compound that we found in the literature in Chikaya-Dachi's group. So this is kind of the proof of concept of a lead optimization type study, so to speak, if I want to use the pharma language, for materials. So that would be the first materials optimization paper that will come out of my lab, of our experimental lab, and we're very proud of it. It's going to hopefully come out soon. In the meantime, of course, we've been working a lot in the software aspects of this. We've been thinking about how to orchestrate the software, manage it, and optimize. So let me we have a package called ChemOS. It's open source. I'm happy to tell you about it. We've been developing, very busy, these optimizers for experiments. And this is something that maybe many of the people in the audience could potentially use. They are all open source, and under this consortium that I have my background here, we'll be supporting much more. We launched a consortium on the self-driving laboratories, not dissimilar to your retrosynthesis consortium, AI for synthesis consortium. Ours is much more focused on the self-driving laboratory aspect, including experiment. And just launched a couple of weeks ago. I'm the director, and we have a staff. You can see the Twitter in the back here, so you can just follow it right now. But part of the consortium role is going to be to keep supporting these packages as we keep developing them. Phoenix, Chimera, Griffin. This is a categorical optimizer that uses chemical knowledge descriptors to deform the space where you're optimizing these discrete variables in such a way that you can use chemical information to inform your discrete optimizer. This is a continuous optimizer, and Chimera is really a good mathematical hack to glue together many different objective functions so that you can say, if I get to my first objective within a threshold, jump to the second objective, I get to the threshold, jump to the third objective, and if I fail, I start going back to the others that I care about. This allows us to build this kind of single objective function that we can send to any optimizer, and then combine many different requirements from the chemists. So let me look at my time here. So let me just tell you about Chimera. So Griffith, sorry. So we did something interesting. This is data from a former Joule paper that we published with Steven Lopez, now at Northeastern University. He used to be my postdoc. We use the same approach, right? Modular approach of synthesis, central molecules, bridge molecules, terminal molecules, to replace fullerene as an organic cell acceptor. This is a data set that is available in that paper, that we threw all the different quote-unquote open source available Bayesian optimizers, and the state of the art is probably GPI-opt, gets to the maximum in average with 11% of the molecules tested. So these categorical optimizers, they look at all the categories and they try to make smart choices. This is complicated because this is basically a combinatorial problem. But you can see that about 10% of the molecules, rather than random searching, which will be 50%, right? You could get to an answer. So that's pretty cool, right? Because the search of these 4,000 molecules, that means that you only need to do 400 to get to the optimum in average, rather than 2,000. So this is the difference between being able to do this automated synthesis or not. But this dynamic griffin is a griffin that actually takes the descriptors that we think are important, like HOMO-LUMO and others, deforms the optimization space, and therefore groups the different molecules together in this multidimensional space. And we get to 6%, which I think is pretty cool. Only 6% of the molecules explored. And we believe that's state of the art because people in the machine learning community have still not done this descriptor-based deformation yet. So you might say, well, Alán, let's compare these optimizers. How do you know if your optimizers are better to Alexei Lapkin's optimizers or somebody else's optimizers, or all the optimizers in the literature like LBFGS, obviously, or grid searches, or design of experiments? So we put together a package called Olympus that is now impressed in machine learning science and technology, where we actually downloaded and got from many papers different experimental optimization surfaces. Actually, Klaus Jensen's group has many as well that we have here and others. And we also added our optimizers and many others. And this is a package where anybody can go in and commit new data sets or new optimizer hooks. And we can basically create tables for our nice papers where we're comparing apples to apples, right? So we don't have categorical optimizers in Olympus yet. Maybe that's the role for a new postdoc. By the way, I'm hiring right now 6 postdocs because many of my group members became faculties everywhere or went to industry. So this is a good moment for any of the 146 people that would like to maybe move to Canada. Please let me know. I'm looking for people. So if you know anybody that wants to do either experiment or theory in this type of stuff, send me directly an email with your CV. Because I'm hiring like crazy right now. Just everybody's leaving. But anyway, in this particular case, this is an example that we did with Merck. It's right now in the Chem archive, of course, going through the different revisions in a journal, where we try to work in scale up, right? We're trying to scale up this chemical reaction, maximize the E-to-C ratio of the Suzuki coupling. Basically, this is work led by Jason High, my collaborator at UBC. We use our software combined to an HPSC and a ChemSpeed, not dissimilar to my own ChemSpeed. Well, this is the one at Merck. And it's basically optimizing several continuous and categorical variables: temperatures, catalyst loads, solvent choices, ligand choices, etc. And here is the results of our second run. We did only 2 runs of about 96 experiments each. And you can see here how our categorical optimizer combined with the continuous optimizer honed in into this ligand 30 and was able to exceed what the humans were predicting over 2 years of manual process optimization. I'm pretty excited about this paper. It shows you that these are things that you can do in industry and it works. Now let's end this talk with interesting forward-looking ideas, right? So you don't want to forget your basic science. And there was this idea that people have been looking for over the years, like, what if molecules could have an inverted singlet triplet gap? Like, is it possible? I mean, it would be kind of like a violation of Hund's rule in some sense, but is it possible to have the triplet above the singlet? That will allow you to relax from the excited state triplet to the singlet and then emit 100% of the light. We found by computational search these 5th generation emitters called inverted singlet triplet gap, or INVEST. In this Matter paper that just appeared, you can see here some of the example molecules that we found. This core was previously found by Piotr Silva, which used to be with Troy Van Buris and MIT, and now is independent faculty member. But they were actually non-bright. So what we did is did a very large search of computational space to find these molecules that basically confer, oscillator strength, these groups. Okay, and this hydrogen bond is very important. Molecules of this type are synthesizable potential inverted singlet triplet gap emitters that could potentially replace these TADF emitters. So this is an example of the point of continuing to do basic science. And in this particular case, we are pushing this very hard, okay? Together with many collaborators around the world, we're working on these INVEST molecules. So what is the future of these robotic labs? Well, maybe you might want to think about automated robot with hands that are moving around and grabbing. For example, this is a tea that I'm drinking here just to survive, giving my talk under the effects of my vaccine. But basically, imagine a robot that is looking at chemical glassware in different positions in the lab and picks it up. So beautiful work by Andy Cooper in Liverpool showed a beautiful robot that was moving around doing experiments all day. But that robot had no eyes. So we set up with Sagi Eppel in my lab create a data set. And it's a beautiful story just about the data set. We had to crawl Instagram, Tumblr, Twitter, all sorts of places. People donated those images of laboratory settings where we later then automated, segmented parts, vessels, what is a foam, what is a solid, what is a liquid, and build a computer, what we consider the state-of-the-art computer vision system to actually detect vessels, which is a very hard problem because they are transparent. But you can see here, this woman putting water in a vessel. You see we can detect the vessel, and we can detect what is a liquid. There's no solids here, but this is funny because it's just a YouTube video that we found on the internet. Okay, so you can throw any YouTube video to our system, and you can see how we perform. I have a graduate student working with our robotics collaborators in the Toronto Institute of Robotics to build the arm that is going to have eyes for this. So stay tuned for that. So that's kind of the future of the chemical lab, in my opinion, this armed robot. And with that, I'm going to end with a picture of my research group. This is Tony Gu, which again, I've been mentioning many times. This is Robert Police working in inverted singlet triplet gaps. Cyril Lavin doing a lot of the theoretical work in this project. Who else is very involved in this project? Andres now became a professor in Mexico. He led some of the synthesis together with Genia, which is here. Gabe Gomez, catalysis. He's now a professor at CMU, starting at CMU. Hao Ping is a computer science graduate student working on the robotic arm. Kazu built the lasers, and I could continue. I would like to say Tim Menke is an MIT grad student, I still mentor in quantum computing, etc. On that note, I'm gonna hopefully pause and have some time for questions and answers. And thank you for your attention.
Thank you so much, Alán. That was awesome. I'm gonna give you a clap. I know we are far away, but hopefully you can hear it. It is truly an honor to have you, and indeed your journey through many different aspects that one can imagine in numerical computing is quite impressive. Indeed, you have presented us half a dozen, if not a dozen, studies all at once, and every one of them is worthy of a 45-minute talk on their own. So again, thank you very much for that. Dear attendees, since you are not able to directly ask questions, please do ask questions by typing them in the Q&A part of the talk. You can also choose to raise a hand, and I'll do my very best to call upon you. I'm going to start by asking the very first question as the questions keep arriving in the Q&A. Well, so Alán, you have shown to us a significant amount of opportunity in utilizing numerics to predict what is the next generation of materials. For example, the inverted singlet triplet materials are extremely unique. The one way, though, that I guess often I look at this as an experimentalist, I love to see that a known problem has been solved using the numerical problem, meaning, identifying a really good laser emitter prior to inventing the new one. Is that, I guess, as a validation, I assume that is a part of the journey that your postdocs go through in the process of knowing that they have indeed reached the optimal way, and then they can take the next step. You haven't emphasized that, but I assume that is indeed the journey that they do take.
Yeah, the first paper that I showed about the lead optimization started with one of the lasers of Chihaya Adachi, and we built around it to show that we can optimize locally around a known molecule, which I think is what you're talking about. So we are going to very soon make high quantities of that molecule, send it to an experimental collaborator, make a laser, and show that hopefully that laser is better, okay, in terms of the critical parameters for the model that go into the device. And let's see if the device really works. We'll send them 4 molecules, so hopefully one of the 4 at least is good in the device. But the other laser molecules that we predicted already by using this categorical optimizer with this Griffin and Chimera together have already shown us very strange new architectures, right? They are actually winged instead of linear, and they have a very interesting properties, but also we now constrain them to be easy to synthesize. So some of them are like 2 steps, very simple steps. So that laser I'm dying to make very soon, and then show that we can also go to new molecular classes. So, but that's correct. We have, for example, in my robot, we have shown the PL emission of known standard molecules, and we just run them, and we know that we get the right PPTP timeline, time scales, and so on. So there's a lot of calibration and explorations around certain spaces before you move into new spaces, and that has been kind of our journey.
Well, the molecular design is one element, right? Once you have the molecule and it lands and forms a thin film, it might aggregate, it might form exaplexes. Clearly in solution, you can predict with a single molecule what the lasing action would be. Is that next step of forming a thin film also a part of the, yes?
we did a paper, and I'm idiot because I removed the slides recently. We have a paper in Science Advances last year with Jason Hine. We did a self-driving lab for thin film lasers, and we did a whole transport layer, an HTL. And we were optimizing basically two variables, basically the amount of dopant and what was the other variable? The annealing temperature or the annealing time, I forget. But the robot basically was building the thin film, taking a photo of it to check if there were cracks, and actually doing a 4-point testing of it. And we did it several times in the robot of Jason. I imagine the future will be to have also those device labs. So I could imagine extension of my lab later to a device, automated device maker like such as that one, and then start making tons of cavities with my molecules inside of them, and just like as the 46 come out, pick the top 5 and robotize the synthesis of those 5 devices. And for each device, there's a lot of optimization. So Christoph Brabeck in Germany, which you know very well, he and I wrote a European grant. I'm gonna get you guys jealous because the Canadians, we can apply for European grants, these ERC grants of the year. So we wrote an ERC grant together. We didn't get it, but we wrote a grant where the idea was he runs his optimizer robot there on my molecular candidates here, right? So we hopefully will resubmit. We were finalists, but that's kind of the thing I want to do. I want to have a device maker. And as you know, Christoph even has a little mini factory, right? So my dream is to go all the way over there.
All right. Well, let me ask you a question. This is from Kiarash Gordiz. Can you explain how much should we, scientists, know about the physics of the problem to achieve an optimum solution? In other words, what percentage of the work is on the shoulders of the machine and what percentage of the is on the shoulders of the scientist?
I think it's mostly on the shoulders of the scientist, Kiarash. So the scientists will never go away. A lot of decisions are happening every day about the chemical space that we're going to use for organic lasers. Or the beautiful story of INVEST came from searches that were happening between collaboration between Robert Police, Gabe Gomez, and Cyril Lavin, going through over several iterations and then running the computer and figuring out what happened and then doing more stuff. So the human is driving the self-driving laboratory. The way I like to say it, and I've said it in many talks, so maybe I should stop saying it if you have heard me online, is a quote from Borges about chess. Borges writes about chess, right? That who is the god behind the god that moves the player, that moves the piece, that starts this game of dust and agonies? And I really love that quote of chess because if you really think there is a god, I'm an atheist, so I believe there's no god. But if you believe there is a god moving the player, who is the god that moves the player? So that is going to be you the scientist. It's going to be always setting up the right conditions, the right robot. You're going to build a robot. So what this is going to be more like if you remove PCR from the biologists, or you removed DNA sequencing, what are they going to do, these people, right? So biology labs are completely transformed, and we haven't done that to our materials labs. I argue we're behind several decades, and I think if we do that, material science will have this flourishing era, kind of like a renaissance, similar to the renaissance that happened in biology.
Well, let me then ask you about the, again, inverted singlet triplet. The one obvious answer to that particular design that's extremely exciting, right, is the opportunity to generate, luminescence that is allowed from 100% of the injected charges inside an OLED. Has that been yet demonstrated, or is that the next step?
Making that molecule is hard as hell. That core is very hard. So we joined with my startup company, Chembotics. We joined with several collaborators in Europe, led by Eli Sisman-Cohen, which you, of course, probably know. And Eli and I are working on making our proposed cores and his proposed cores. We hope to have a paper sometime this summer with the first made and tested molecule. We also believe, based on a lot of our studies in the literature, that it's possible that people, including Chihaya Adachi, have made some INVEST molecules They just didn't know they were in best. So we will also be reporting that in that paper. So we'll test them better. We're also doing better spectroscopy. We have to kind of dope with some sensitizers like the spectroscopy to try to make sure that you really are demonstrating that there is an inverted singlet triplet gap. You also have to think about experimentation. But that particular set of molecules, we think, again, there were 2 or 3 cases in the literature where we calculate these molecules, they look like they are in best. So we have to just go and see again and make devices with them. And so therefore, maybe people ran into them, but they thought they were very good efficient OLEDs. They just didn't know they were these magical molecules that use this dynamical spin. Basically, the idea is that the spin physics is in such a way that your HOMO and LUMO have many places where the opposite spin electrons can go. Therefore, that basically destabilizes the triplet with respect to the singlet, and then allows you to have this weird inversion. Okay, so that's the quantum chemistry of it. But the point is, it looks like many molecules that look like TADF. Just if you keep dialing up the TADF-ness, they can become inverted singlet triplet gap emitters.
The molecule is actually quite sizable, so I assume it's evaporatable as well, because typically big molecules have hard issues with being deposited.
Yes. So okay. So let me tell you. So yeah, that core with colecticine has 7 nitrogens. It's very important that it has this nitrogen in the center. We found out for that reason, for the spins to go around. It's the first core found, but my postdoc Robert Police and I are writing a patent application right now we did the computational research of all possible organic rings, basically, that could make this. And now we found very small cores. They seem to be tough to be made, but if we can make some of those few cores that have not been reported in the literature, these are heteroatomic molecules that organic chemists, I think, have been afraid of trying. But if we're able to make a few of them, then they will be way smaller molecules. You will be amazed how small they are. I'm happy to send you one-on-one, once we submit the patent, the pictures of them. And I have tried to collaborate with my colleague, Andre Uding in Toronto, to make them. So hopefully we can make a few and show that they are InVest. But InVest just started. The paper is just accepted online. It's really just the beginning of the field of InVest, hopefully. Yeah.
The other question is regarding your lasers themselves. Are there any, I haven't seen any threshold numbers or call it performance of the lasing dyes. I mean, the dyes are very efficient, PL. Have they been tested as optically pumped lasers at this point?
We test them, we see gain. You know, as you know, sometimes you have them in solution and you can see gain just when they are in solution. Yeah. I don't have the numbers. I apologize. But I can certainly also send them to you because I haven't finished the paper. I don't have the data set in a slide format yet. Yeah. But basically they are going to be lasing because they're variants of Chihaya, our first paper, and then the other ones hopefully are going to be lasing too. I mean, we are very confident about the predictions, and in solution, I think we're going to see them lace most of the time. It's the problem, of course, when they go to the device, as you say, all sorts of stuff can happen. And they could degrade as well, oxidize, etc. Of course, we also screen against oxidation, but all sorts of things could happen in the device that react with the host. Who knows? You know, like aggregate, whatever. So we have to see, or not be evaporatable, as you say. So yeah, it's gonna be a long journey. It's gonna be a long journey. We are like Chihaya in 2012.
Well, but you do have many, many options that you can numerically, hopefully very quickly predict. This is from Ali Malihi. Are you working with the oil and gas industry, and can you give a business case examples for applications of representation modeling for molecules? Any thoughts on that?
My startup company, Kevotics, which by the way is based in Massachusetts, has some collaborations and has done some collaborations and work with the oil industry. So Kevotics has done it. Having said so, we just launched this consortium that I'm just showing you here in my screen, where we're inviting companies and researchers in all these areas. So if you're an academic researcher that wants to participate in our consortium, or if you are a company, you know companies in this space, let us know. I mean, we're helping all sorts of different players, from biotech to we believe there is like, the consortium has the premise that these self-driving laboratories have all these pre-competitive things that we need to do. Data handling, optimization, data analysis that we all need to make all these applications happen. And of course, the oil and gas industry is nothing different, right? So for example, Kevotex just announced a partnership with Syngenta for agriculture molecules, right? So that's another example, agtech. So there's a lot of areas where you can actually make progress by using AI and robotics in material science and molecular science. So Ali, if you have any ideas, just shoot me an email or a Twitter DM, and I'm happy to hear what you have in mind.
Well, Alán, thank you so much. It is fantastic to have had the chance to share this time with you. Those of you who are looking for an exciting research group to join, Alán has mentioned that he has openings for 6 postdoctoral positions. I strongly urge you to consider them, as indeed he has an incredible amount of stamina, as you can see from his presentation, and also just a brilliant number of sets of inventions as well as directions that his group has been taking and continues to take. So Alán, with that, again, thank you tremendously for joining us today. I will just conclude by letting you know that the next Nano Seminar is coming up on May 17th. It's going to be delivered by Rehan Kapadia from USC. Title of it is Hot Electrons, Cold Materials, Building Blocks for Next Generation Semiconductor Devices. I very much hope you'll be able to join us May 17th. See you till then. Take care.